The linear momentum conservation holds in any frame of reference. It is not specific for a single frame of reference, such as a center mass frame. It works always. The linear momentum conservation is a direct consequence of Newton's third law. If you sum the force between the two particles, then because the action and reaction gives the magnitudes of the two forces the same but opposite, therefore the delta P momentum transfer to a single particle 1, 2, 2, delta P1 and delta P2, the particle 1 and particle 2, if I sum these two, it is always 0. So sum of two momenta, if there is no external forces, then it is always a 0. That means P1 plus P2 as a vector, this is always constant. And it is true for any number of particles. So let me pass. This is advanced level. However, if you have time, just have a look at it. This strange equation is actually the same as F equals ma. And this one, this is kinetic energy minus potential energy. And if I take the velocity derivative, only this one contribute. This one is a momentum. And take the derivative, that is a ma. And what's that? Gradient of kinetic energy vanishes, gradient of potential energy minus the gradient potential energy. That is a force. So this equation looks very strange. However, it is nothing but this one, vector. That means F equals, this is a force, F equals ma. What is that? That is a time derivative of linear momentum. The same kind of equation is called Hamilton's equation. Let me tell you Hamilton's equation. And Hamiltonian H is nothing but the sum of P squared over 2m, that is kinetic energy and potential energy. And you will find it is we have first order coupled equation. So this one is also exactly the same as F equals ma. This kind of problem is very important in this chapter. And the linear momentum conservation. This is the initial state. They stick together with the same velocity, and suddenly this rubber band is broken and they move separately with the different momentum. The interaction between these capital M and small m, they are internal forces. Therefore, during this process, internal force does not change the total linear momentum. So total linear momentum, initial state, they are moving together with this velocity. So this is the total linear momentum of the initial state. And what is the total linear momentum in the final state? That is just a sum. And this sum must be the same as the initial value. This is the total linear momentum conservation. At the center of center of mass frame, center of mass frame and center of momentum frame, they are exactly the same in classical mechanics without relativity. But when we consider relativity, center of mass frame is not well defined. Instead, center of momentum frame is a very nice frame of reference. In the non-relativistic case, center of momentum frame is exactly the same as the center of mass frame. Anyway, conservation of linear momentum gives the initial value, final value the same, and this is a way how to find out the center of mass velocity. You have divided this factor. There is another important, this is a very important, and in the text of X12, I have written the how to describe the two-body problem, and a long time ago, we have studied the reduced mass. Reduced mass. Reduced mass always appears in the two-body system at the CM frame. At the CM frame, two particles collide, or after collision, they move opposite direction. And CM frame, that is the center of mass or center of momentum frame, at CM, TCM, that is total mass multiplied by the center of mass velocity, they are the same. But at the CM frame, they are the same, and it is actually 0. That means if two particles are at the CM frame, the momentum, linear momentum of the total linear momentum, sum of these two momentum must be always 0. Therefore, you remember we have mass M and capital M, and what is the center of mass? This one is X1 and X2. Then M1, X1 plus M2, X2 divided by M1 plus M2. This is the center of mass. And you remember the distance from a particle to the center of mass and distance from this center of mass to the other particle. The ratio is opposite. M2 small f, remember, right? So distance, if it is a heavy, this distance on, right. All right. And you will find this is the relative velocity, subtraction of the two velocities. Why? At the center of mass frame, two-body momentum has this kind of form. One is a mu r dot, and the other is a minus a mu r dot. And what is r? R is the relative coordinate, just the difference between the two positions. Difference between the two positions. And if I take the derivative, what's that? The relative velocity of the two particles determines the r dot. And this is the reduced mass. Reduced mass is the product divided by sum. You will find this is a particle momentum of the particle with the capital M. This is the momentum of the particle with the small m. Remaining factor comes from the center mass formula. The distance between the center mass to this object is this and this ratio. So center is very heavy and very light. Center mass is near to capital M, right? The distance is opposite ratio, has the opposite ratio. That's the reason why the overall factor, mass multiplied by this distance scaling factor, If we multiply both of them, this factor becomes identical to each other. That is the reduced mass. So reduced mass is the same and relative velocity is the same except for the sign. So that's the reason why we had better choose the center of mass frame, that is center of momentum frame, to describe the collision problem of the two particles. It becomes a very simple one-dimensional. It reduced into a one-dimensional problem. Always remember this, and this one is just not the distance from the center of mass to particle 1, center of mass to particle 2. This R is the direct displacement between the two particles. Not this, but the whole amount is R. Okay, so that is called the relative coordinate vector. Here, let us see this problem. We have two particles and collision point. Two particles of capital M, small m, were initially at rest. And this is the collision point. What is the initial total linear momentum? Total linear momentum at the initial state is capital M plus, what is the velocity? Zero vector. Aha, it is 0. That means in this frame is the CM frame. Center of mass is not moving. This is capital M plus a small m multiplied by center of mass velocity, and this is 0. So center of mass is at rest. That means this frame of reference is the center of mass frame. In the center of mass frame, we can always use this formula for the two-body momentum. And remember the distance between the distance ratio, this distance and this distance. This is the collision point. At the collision point, the particle merges, capital M and small m merges. The final state is m plus m at rest. Its momentum at the collision point, they are still at rest because we are in the center of mass frame. The center of mass is the same. So collision point must be the center of mass, and it is trivial to find that the distance ratio is a capital M and small m, right? And we have another interesting problem. This is the two particles. For example, is a red ball and red ball and red ball and blue ball and blue ball. They collide and scatter, for example. Red ball and blue ball, they collide. Blue ball, they collide, and this is initial A, B, and the final velocity C and D, something like that. To simplify our analysis, I have chosen the mass to be the same. They are two identical particles. So in the formula for the momentum conservation, linear momentum conservation, initial momentum, final momentum, I have divided this mass already. And then we have this interaction is a totally elastic, unelastic scattering. That means elastic scattering means this is true. Momentum conservation is true always. However, elastic scattering also requires the energy conservation. Sure, I have divided this 1/2 m, 1/2 m, because 1/2 mv squared, 1/2 mv squared, 1/2 mv squared. So every 1/2 m has been removed in the equation. So we have this is a vector equation, and this is a scalar equation. This is a linear momentum conservation. This is a kinetic energy conservation because the elastic scattering. Let me square the left and right side of this, and you know how to expand this. That is a squared 2 times a dot b plus b squared, and c plus d squared is in a similar manner. And subtract this squared value with this a squared plus b squared, c squared plus d squared. Then these terms vanishes. In the next semester, when we consider the Compton scattering, we will use this expression again. And anyway, if I make a subtraction, quadratic terms disappears, and we have factor of 2, and they cancel. A dot b becomes c dot d. It is very convenient to make use of the center of mass frame. At the center of mass frame, they collide together. This magnitude, this identical part, this magnitude, these two magnitudes must be the same. Why? At the center of mass frame, a plus b must be 0. This is actually divided by this is just divided by, for example, ma plus mb should be the total linear momentum, and vcm must be multiplied by 2m. So divide by 2m, then it is 1/2 a plus b. That is the center mass velocity. This center of mass velocity vanishes because we are at the center of mass frame. So in that case, A, B, they have the same magnitude but opposite. C and D, they have the same magnitude but opposite. The magnitudes are the same. So it becomes trivial. These velocities are non-zero, and they are all equal in magnitude. Now what happens? Not in the center of mass frame, but in a fixed target frame. If you play a billiard ball, then you have a, I don't remember, white ball, red ball. You hit, this is a fixed target. The initial velocity is 0, and you hit this ball, and then this one initial velocity of the white ball is non-zero, and initial velocity of the red ball is always 0. That means this one is called fixed target. In that case, this b is always 0, and you will find the c dot d is 0. If c dot d is 0, and both the c and d are moving after collision, they move together, then the only solution is that this scalar product cosine theta equals to 0. That means the scattering angle should be the right angle, 90 degrees. So this is another simple application of this elastic scattering using this vector algebra. Okay. This is for the linear momentum conservation for a system of many particles. And you remember, net force on a single particle is the sum of the net force due to the external force and internal force. Internal force means this is a system, and this is ith particle and jth particle. They interact. this is n particles, and this is called the internal force. But Newton's third law states that the force between any two particles, if we sum these two forces, they are the same in magnitude and opposite, and therefore the sum is 0. So whenever we have a vanishing external forces, internal force contribution always vanishes. That's the reason why the total linear momentum is conserved. Because this is a 0, total linear momentum is conserved if there is no external force. The net force on the system of particles must vanish. That means total linear momentum is conserved. So you have to remember the mechanism of the conservation. So let's read the final problem. Oh, that is not a final. This is a very interesting problem. This is a rather simple problem, and this is the 14 is a very interesting problem. We make use of the center mass frame. Then this problem is solved quite easily. Initially, this one is at rest, and initially this small box is on top of the left edge of this long bar, and its initial velocity was capital V. It was moving very fast, and there was a kinetic friction between these two, okay, and there is no friction on the bottom, and this one can move free. It looks a very complicated problem, but if you are looking at this problem at the center of mass frame, then I told you at the center of mass frame, you can always express as a one-dimensional problem. And the momentum of the two particles are always the same except for the sign. And this r dot that is called the relative velocity. The r dot is the relative coordinates, the time derivative. This is the relative velocity of the two particles. So that method is applied to solve the problem. Let me tell you this one. You are familiar with this. The velocity looks rather different, but if you multiply the mass of A is a small m. If you multiply m, then you have m. Mass of the B is capital M. Then this and this, they are the same in magnitude, and only the sign differs. So this is a two-body problem with the reduced mass m plus m, this method, and the relative velocity. Here, this is capital V. Why only the capital V appears? It was at rest. The relative velocity between the two objects is always the same in non-relativistic problem. So initially the relative velocity was a capital V. That's the reason why we have this V rather than V minus V capital V minus small v appears in the rather complicated problem. It is a more general problem. However, at the center of mass frame, this one becomes very simple. So if you can solve this problem, you have understood the total linear momentum conservation completely. And The formulas I use to solve these problems are a very trivial one we learned in the early stage of this semester. Okay, let's take a break for 10 minutes.